Uh, I'm going to share my presentation. Uh, Can you see my screen? Not yet. Okay. I'm coming. Okay. I'm going to be disconnected and connected again to allow the presentation. Okay. Can you please see the presentation now? Can you see my screen
Yes, we
now?
can see. Yes, sir. Yes, sir.
Okay, perfect.
see.
So my presentation focuses on a subnational age structure modeling approach of malaria transmission and burden. Some issues. So I'll focus on the background of the
Hello,
study.
Prof. Sir.
Yes?
It's not yet in presentation mode, sir. Full screen.
Okay,
Probably if you
let
put it in.
me check.
Presentation.
I think it's this
Full
one.
screen mode.
No, not
Full
yet.
screen mode, sir.
Come again?
Full screen mode.
Yes, that's what I did.
Yes.
That's what I did this
Okay.
time.
Oh, okay.
Okay.
Okay, we'll use this, sir.
Okay.
Go ahead, sir.
Okay. So I'm going to present the background and afterwards the model framework, some application of the model on 4 African countries and conclusion. So malaria transmission vary significantly across administrative units, even within a same country. And therefore, national estimates mask this as strong variability and age-specific variation. Also, most impact of control strategies against malaria depend on the local transmission intensity, depend also on the age cohort, and also the different control strategies implemented and the immunity of people. And nowadays, policy decisions require information on malaria dynamic at administrative unit, not at national level. And about age structure, we all know that children under 5 are the most vulnerable to malaria and bear the highest malaria burden. Why? Because there is a gradual immunity builds up, and the implication is that subnational model is very, let's say, important to implement efficiently control strategies, and also a structure model help in efficiently evaluate some interventions like vaccine, which targets under 5 children, first 2 years children, and also seasonal chemoprevention, targeting under 5 children. So the subnational model that we built is an extension of a recently developed national model of malaria transmission, accounting for vaccine and non-vaccine intervention. So you can see on the screen the flowchart that is considered. So for each of the age cohorts from 1 month to 100 years, this flowchart was considered, and we can notice 4 different emphasis compartments: asymptomatic individual, uncomplicated malaria, severe malaria, and admission to hospital from severe malaria. And we distinguish between in community case fatality ratio and hospital case fatality ratio. So the ordinary differential equation focusing on the temporal dynamic and the aging of individual. Now, moving from this national level model to a subnational model require some parameterization techniques. So here I distinguish between parameters which vary according to administrative units and parameters which can be considered as fees at the country level values. So about the spatial heterogeneity parameters, we have the entomological inoculation rates, which vary considerably across administrative units, and the proportion of emphasis mosquito, and of course the death rate for severe cases in community death rate and hospital death rates. So these parameters vary according to administrative unit within a country. And about the non-spatial heterogeneity, we have, for example, a proportion of clinical cases that progress to severe cases, immunity parameters, probability of developing symptoms after malaria infection, and the recovery rates of asymptomatic individual. Most of these parameters depend on the immunity of individual. And how we derive the subnational entomological inoculation rate. We use an approach similar to that of Smith and collaborator 2005, and we derive the subnational entomological inoculation rate considering local malaria prevalence. And we link this with the country level entomological inoculation rates. So using expression 2 and 3. And in this expression, what is interesting is the parameter B, that is the degree of a spatial heterogeneity in the distribution of entomological inoculation rates across administrative units within a country. We also consider the proportion of emphasis mosquito. The proportion of emphasis mosquito is used to derive the biting rate from the entomological inoculation rates. And this proportion of emphasis mosquito varies according to the administrative units. Due to the variation of local malaria prevalence. So we consider the expression in 4 where this parameter is computed per administrative unit considering the population weight, W, and also considering the prevalence. And what is also interesting here is the parameter gamma that represents the degree of spatial heterogeneity in the distribution of this proportion of emphasis mosquito as for the entomological inoculation rates. Now, how did we approximate the subnational death rate and death rate for severe cases? We start from the case fatality rates, considering the observed death, malaria death, and observed clinical cases in each administrative unit. We consider the case fatality ratio, overall case fatality ratio for severe cases. That is the sum of all deaths over the sum of all clinical cases. But we know that clinical cases do not lead to malaria death, only severe cases. So we need the proportion of clinical cases that progress to severe cases. And this parameter is considered in the denominator to avoid having 0 at the denominator. Sorry. Okay, so to avoid having 0 in the denominator. Community treated cases. So we derive from the overall severe cases, the community treated cases and hospital treated cases, considering the probability of being admitted to hospital. So from this probability, we can derive the hospital case fatality rate and the community case fatality rate that we suppose are time the hospital case fatality rate. So from this 2 case fatality rates, since there are probability and we want a death rate in the ordinary differential equation, we use the exponential survival model theory to derive the death rate, hospital death rate, and in community death rates. And afterwards, we also considered non-vaccine intervention, the three main non-vaccine intervention, so long-lasting insecticide nets and indoor residual spray and seasonal chemoprevention. So for the insecticide net, we consider that the net reduce the biting rate with a use lifetime that is still 3 years. So after 3 years, the net is renewed. That's the reason why we consider modulo here. And we also consider that since the net is an insecticide net, so the net also increase mortality rate. So using expression 8, and considering the indoor residual spray, we consider that the spray also increase the mortality rate. So we use a combined effect of the insecticide net and the indoor residual spray to have an increase in the mortality rate of mosquito, considering that there is an exponential decay of the efficiency of indoor residual spray once used. Regarding the seasonal chemoprevention, we consider that it reduces the age-time dependent force of infection for children from 3 months to 59 months. And we consider different rounds of the application of this intervention, and with an efficacy that decreases in time using an exponential decay function. So illustrated by expression 9. We also consider immunity in the model because immunity plays a significant role in malaria incidence and death. So we consider maternal immunity because some studies show that immunity is transferred to babies from mother at the very early age, before 6 months. So, and this immunity decreases, and we consider, following malaria literature, we consider an exponential decay of the maternal immunity. And we combine, of course, this maternal immunity with the natural archaea immunity. And this is illustrated by expression 10, 11, and 12 that also accounted for the time-dependent entomological inoculation rate and the life expectancy. And from the expression of the immunity and following the excellent work by Felipe and collaborators, we show that immunity acts at the level of the probability of developing symptom, at the level of the recovery of asymptomatic individual, and the warning rate of archaea immunity. So we express the probability of developing symptom in the function of immunity using expression 13. And regarding the recovery rate of asymptomatic individual, still following Felipe and collaborators with the epidemiological studies, we express the recovery rate of asymptomatic individual as a nonlinear function of the immunity, expression 14. And the warning rate of acquired immunity is still following Felipe and collaborator, which show a clear relationship between warning rate and acquired immunity. We use the expression 15. So we updated the previously used expression in the recently published national level model, considering here the immunity instead of the age-time dependent force of infection. And we also consider the rainfall seasonality, because rainfall impacts the birth rates of mosquitoes. So we express the recruitment rates of mosquito in the function of the peak of rainfall in a year, and also the lag effect, because it's not when the rainfall, when we have high rainfall value that the recruitment rate increases or become the highest. It requires a time. That's the lag effect, generally 1 month. So we also account for the seasonal function of the rainfall, and now the calibration of the model. So to calibrate this subnational model, we start with the country level fitting. So what we notice is that there is a great inter-annual variability in malaria cases and death. And this can be only explained by an inter-annual variation of the prevalence. So instead of considering a constant entomological inoculation rate in the model, we consider a time-varying entomological inoculation rate, considering the interannual malaria prevalence. And we can also see here that national B is the degree of heterogeneity in this in the distribution of the prevalence, considering the historical periods. And we also consider a time-varying death rate, so linking death rate to time-varying case fatality ratio, and using a country-level proportion of clinical cases that progress to severe cases. And when we finish with the country-level fitting, we focus now on the subnational fitting, where we compute the subnational entomological inoculation rate, malaria mortality, considering the proportion of severe clinical cases that progress to severe cases for each admin 1 unit. And with this, we consider that all the other parameters are constant across admin 1 unit within a country, and this at the country level estimate from the country level model. And then the transmission model at the subnational level was then run independently for each admin 1 unit. Now, the big issue here is that aggregating simulated subnational cases does not yield exactly the country level estimates. Why? Because of the non-linear characteristic of malaria dynamic. So to enforce the subnational cases and death, so that when we sum them, it yields exactly the country level estimate. We use a normalization process where we compute a ratio, RC and RD, RC for malaria cases, RD for malaria death, and RC is the country level estimate, so not reported, country level estimate over the sum of all admin 1 units. And same thing as for death. And then from this value, we can now rescale the malaria cases and death at a national level, subnational level. So we rescale the malaria cases at subnational level and malaria death. And since we can do this only for the historical period from 2000 to 2024, we use the trends of this ratio to model the value of the ratio of the two ratio in the function of time, using these two expressions where we have lambda C and lambda D, which indicate the speed of change in the ratio. So we estimate these two parameters using historical values. And we calibrate the model computing not only parameter B, but also parameter gamma. So parameter B is the degree of spatial heterogeneity in the entomological inoculation rate, in the distribution of entomological inoculation rate. We also consider parameter gamma, which is the degree of spatial heterogeneity in the proportion of infectious mosquito. So we calibrate these two parameters using the root mean square of observed and estimated and rescaled malaria cases and death. Consider a weight to have the same magnitude for cases and death. So by minimizing the root mean square, we estimated B and gamma. Now, application of this new subnational model. We consider 4 countries, high transmission countries like Benin and Burkina Faso, and low transmission country, Ethiopia and Somalia. We use data on malaria burden. We download the data from the Malaria Atlas project the website there. And we use MATLAB to code the model. And the model, the codes are available in my GitHub session, but not yet public because I'm on the way to submit the manuscript. It's a very new model. So at a country level, we can notice here a good fit of the model. And at the subnational model, so the parameter estimated, table of the parameter estimated, where we have the country level entomological inoculation rate, the proportion of clinical cases that progress to severe malaria at a national level, immunity parameters, and also the root mean square for the country level model and for the subnational model. And we show here the fits of the model comparing reported and estimated malaria cases at the subnational level. So the 12 administrative units in Benin, and also the same as for Burkina Faso, for Ethiopia, and for Somalia. So we can see overall good fit of the subnational model. And here we show the case fatality rate of malaria at the subnational level for Benin and Burkina Faso, high transmission countries. And we can see here that there is a great variability in the entomological inoculation rate across the admin 1 units. So from 90 to 130 regarding the EIR, and for the case fatality rate, also great variability. What is interesting to notice here is that there is no link between the variation of the entomological inoculation rate and the one linked to the case fatality rate. And this is very interesting. It means that local transmission cannot explain alone the case fatality rate. And there are other factors like case management and also immunity parameters, and most importantly, control strategies implemented, which vary from one admin one to another. And we have the same trend here for Burkina Faso, where we see a great variability across admin 1 unit. And the variation are not similar. And for the low transmission countries, we notice first that the entomological inoculation rate, estimated entomological inoculation rates, are very lower than the high transmission in the high transmission country, from 8 to 30, less than 30. And same thing as for the case fatality rate, that is relatively low in the low transmission country. And we can see a great variability in entomological inoculation rate and case fatality rate in Somalia, greater variability compared with Ethiopia. And we also consider projection over 2050 of the cases, malaria cases, and death, distinguish between the whole population and under 5 individuals, under 5 children. And we can see here a great variability across admin 1 unit, relatively same magnitude of malaria cases for the whole population and the under 5 children. So we notice that regarding the death, we notice that under 5 children bear the highest malaria death in red. But in Burkina Faso, we can see that we have the same magnitude for the whole population and the under 5 children. And the variation is not so important across administrative unit compared with Benin. For the deaf, what we notice is that higher deaf in under 5 children, but from 2020, 2023, we have almost the same value for malaria death for the whole population and under 5 children. And this is probably linked to the control strategy implemented in the country. For the low transmission country, Ethiopia, we also notice great variability across admin 1 unit for case and death, and similar malaria case and death for the whole population and under 5 children, and also similar trends for Somalia. Now, a key insight from this study, we can notice that malaria burden is highly heterogeneous within countries. And also, case fatality rate does not follow transmission intensity. We have some high transmission setting with lower case fatality rates and low transmission setting with high case fatality rates. And for policy relevance, we can say that national estimates are very insufficient for an efficient malaria control in African countries. So we need a geographically targeted intervention, focusing on administrative units and focusing on the age-specific pattern. And this new model is very suitable to evaluate the vaccine impact. Why? Because vaccine targets target under 1, let's say under 2 children. So the first dose at 9 months and the booster dose 1 year after. And the model also a low long-term projection to, let's say, evaluate the dynamic of malaria over 2050, even 2100. Thank you very much for your attention.
Prof's presentation, then our participants online too. If you have 1 or 2 questions based on Prof's presentation, let's do that by signifying raising of our hands. Anybody physically here who wants to ask a question? Okay, 1, I have 1, I have 2. Okay. The first person. Let's have you, sir.
Yeah. Thank you very much, Prof, for your wonderful presentation. Prof, I want to find out the state, I didn't get that clearly, how you moved from the derivatives, the differential equations you got from your flow diagram to subnational. And the second question is, what is the choice of fitting in only for some parameters? You talked about subnational fittings, and you made use of just 1 or 2 parameters. So I just want to know. Thank you very much.
Okay.
Prof, you want to respond? Yes.
Yes. Can I answer the question?
Yeah, go ahead, sir. Go ahead, sir.
Okay. So to answer the question, I want to go back to the presentation. Sorry. So, okay. So considering okay, there is, yes, there is even an issue with the ordinary differential equation, but it's not really important. So you can see here that we account for a temporal dynamic in each compartment and each aging. So the question focuses, I think, on the aging. That's very important. You know, people, of course, grow in age. So we consider in the model a monthly age step. A monthly age step. This means that when the model starts, at the end of a given month, some individual will move from age cohort X to age cohort X plus 1. So this means that with the differential equation, normally when we use this and this, we cannot have again minus SH. So the minus SH that is here is simply to show that at the end of the, let's say, of the time time unit, so the monthly time unit, all individuals in the compartment move to the next cohort. That's the minus SH minus EH minus ISH. And some, of course, will enter the next cohort. So the model will be recruit here, recruit 1 plus all this minus SH. Recruit here EH plus all this minus EH. Why? Because we are considering the same time unit for the aging and for the step. So consider that we consider a monthly time step. Since we consider that a monthly time step, this means that after 1 month, all individuals in the age cohort, because we also consider monthly age cohorts. So monthly age cohort and monthly time step. So at the end of each time step, all individuals in the compartment move to next age cohort. That's the reason why we have minus here, minus normally everywhere. And we have recruits everywhere here, recruits. So this is a contracted, let's say, ODE, where you cannot see the recruit here. You cannot see any recruit here. And we should normally suppress the minus since we are using a contracted ordinary differential equation. So it's a mistake when I was making the presentation. So that's what I can say. It's very simple to do if you consider the same age cohort, the same age cohort, monthly age cohort, and monthly time unit. So you can develop the contracted ODE by considering the recruit and those who move out from the compartment. Now, the second question is about the subnational modeling strategy, where we consider some parameters here some parameters which vary across admin one unit, and other parameters like humidity parameters which are considered fees at the country level at the country level values. So why? Because parameters such as proportion, for example, of clinical cases that progress to admin one, that progress to severe cases are, let's say, parameters which are not affected by a sub-administrative division. They are strictly epidemiological parameters. So all individuals within each country will have the same value. And this is supported by numerous malaria literature, malaria studies. So based on this study, we fix all these parameters. For example, the humidity parameters. We consider that all individuals in a given country have an immunity that is linked to the age, for example, but not to the geographical position. And this is demonstrated by many studies on malaria epidemiology. So that's the reason why all these parameters are considered fees at the country level values. And the only parameter that vary across subnational units are the local transmission intensity and the death rates. Why? Because of the control strategies which vary across admin one unit. So this is supported by many studies on malaria. So that's what I can say about the question.
All right, so we're going to take the second question for. Okay,
yes.
Thank you very much, Professor Lele. I have one or two comments and then maybe one question. Now, I was thinking that like since you are working on various locations in Africa, I don't know whether you considered the national malaria strategic plans for some of those countries so that you can tailor your questions and your concern in your model what's obtainable in those countries, because you are dealing with different countries from West Africa to East Africa, as I can see in your slide. That's number one. Number two is I was looking at you in one of your graph. You mentioned something on malaria. I mean, burden. And also, I mean, when you talk about burden, it's a very broad stuff. When you say burden of malaria, it means that you are talking of mortality, you are talking of incidence, you are talking of prevalence. So I don't know how you post this from you. I would like a further light on that. And then the last one is I was seeing a partial differential equation there. So, and you are looking at age heterogeneity. I don't know if I'm right. So, but yeah, so I feel that that may be very, very quite a complex model, because if you for most epidemiological model, you find out that the classical ordinary differential equation that is discretized. If I want to have can have different classes, and then I'm also having a kind of evolution of different age from one age to another age. So I think maybe you can compare this kind of model instead of using the PDE part. You can look at, I don't know if you have thought about it, looking at it in form of a differential equation where you partition each people from different age, maybe age 0 to 5. You have a model, you have a particular model, maybe SCIRA, and then they evolve from that 0 to 5 to another age, adults. Maybe you have 2 age classes, the young and the adults. So there can be an evolution from 0 to 5 and then to adults. So, and then this one can capture the dynamics of that malaria better. I think from my own, our own personal studies we have been doing that. Over.
Prof, you might want to respond to that, sir.
Yes, thank you very much for this very interesting question. So the first question focuses on the malaria strategy plan, malaria control strategy plan. And, I'm working with Imperial College London at the Vaccine Impact Modeling Consortium. And this study was, let's say, was funded and asked. So they asked me to develop a model that can be used following very strict guidelines. So, they consider, of course, the malaria control strategy plan for each countries, and they, let's say, develop some guideline. We want this, and this. And it's based on all these, let's say, item in the guideline that I developed the model, So I can say that, yes, it's follow the malaria control strategy plan. Now, the second question, very quickly, again. So the second question is about the model, the age structure model. It is a very complex model. Why this model? They want a model that focus on each monthly cohort. So let's say putting together under 5 children, for example, from 0 to 5, from 5 to 10, and so on, will mask intra-variability in this large age cohort, But we know that vaccination targets 9-month cohort and 1 year after the booster dose, So it's important to have the dynamic of malaria in each monthly cohort, from 1-month cohort to 100 year. Yes. So it's a very complex model, but the advantage here is that it's helped to know exactly the dynamic of malaria in each age cohort. And when the vaccine is introduced in the age cohort, how, for example, babies who are vaccinated at age 1 or 9-month cohort, how this vaccination acts in the future, considering the decay of the efficacy of the vaccination. So putting everything together to have large age cohort will not help to really, let's say, capture this, let's say, dynamic. So that's the reason why what they asked me is to have the dynamic of malaria for each monthly cohort. So that's the reason why I consider such a model that I recognize very complex, but very accurate compared with other model.
All right, thank you very much, Prof. Thank you very much. So we are going to take Prof's remark. Yes, sir. Take it.
Thank you, Professor Glele. Professor Glele has been a collaborator. We have supervised some students from his lab at LabF at University Abuja Calabre. And we are still working together. I want to appreciate you for coming. He's very, very busy, and out of his busy schedule, he has find time for us to. He was supposed to be here physically, but due to some meetings in Benin, you know, Benin is not far from Nigeria. You just need to cross the border to Lagos. Am I right? And then you move to the airport. So I told him that he would just take a cab from the airport, from Benin, and then go to Ikeja, enter flight to Akure, and then come. That was our plan initially, because the last time he invited me, he got a vehicle for us from here to Benin, and then they took us inside the border, and then we entered, and you know. So thank you very much for coming. We really appreciate you, and I want everybody to give him a round of applause.
Thank you. Bye-bye.
Thank you very much, Prof. Thank you very much. All right, so while the keynote address was going on, we have one of our very own dean come in. So that's the person of the Dean of Faculty of Physical Science, the person of Professor CEO Akintayo. She came in, so we are going to be receiving her shortly to give her a good week. Can we put our hands together for you?
Thank you, the moderator. Good morning, everyone. It's with great pleasure that I bring greetings from my faculty, the Faculty of Physical Sciences, Federal University, Oye Ekiti. I want to welcome you all, distinguished scholars, our professors, the convener, to this important conference. I know to many of us it will be an eye-opening conference, especially for people that are coming for a conference like this for the first time. I want to use this opportunity to really appreciate the convener, Professor Bakare, for the good job you are doing. If we can have just 5 more of his kind here, I would know that 4 years in yes, so we really want to appreciate you, sir. And we want you to bring more. 4 years is always ready to receive conferences like this. And to our supporting professors, especially Professor Oyedeji. Wherever you see Professor Bakare organizing a conference, that man has to be there. So it's like the backbone. We really appreciate you, sir. So, Prof is from the life sciences. You know, we have 3 in 1 year with so we have physical, we have life, and we have computer. So Prof is in life sciences, but is very, very supportive. Very, very in everything, anything progressive, you will say. So I want to appreciate his work. Thank you so much for coming. I appreciate the team too. The team, you are doing marvelously well. I do see your posts, you know, if you're having conferences or things like this, and we're always proud of you. And we know of exploits that you are doing and you will continue to do. So, and I pray that we younger ones that are coming on board, being a lecturer is good if you are a scholar. Or if you are a lecturer that is always looking for shortcuts, the hand is not always palatable. But if you are a scholar, your visibility, everybody will know about you. So please, the upcoming ones, please tap from the, what will I put it now, Prof? Tap from the anointing. Professor Bakare's anointing to win grants. I wish you a very successful deliberation. And to all our invited guests, please thank you so much for coming. We really appreciate it. So, wishing you a very productive time and a very beautiful deliberation. Thank you very much.
Thank you very much. All right. So thank you very much, Ma, for that wonderful message. All right, so we'll be having our next keynote address, and that's the person of Professor Chakravarti. So reading His citation will be Miss Ismail Happiness. Can we put our hands together for her as she comes forward? Okay. Are we?
Postpone. The full screen. She can. It's on screen. Let's come on the screen. It's going to go on screen. That's it. Yes, you need to present it. John is there. Professor Chakravarti. This is nice. It's really. Yes, I've done it now. Project.
All right, he's online, so his video is coming up shortly. Yeah, so can go ahead.
Okay. The citation of Professor Sneashish Chakravarti. Professor Chakravarti is a distinguished mathematician, academic leader, and internationally recognized researcher in the areas of applied mathematics, machine learning, structural dynamics, and computational modeling. He currently serves as professor in the Department of Mathematics at the National Institute of Technology, Rourkela, India, where he has played a pivotal role in advancing academic excellence, research output, and institutional governance. Professor Chakravarti received his Bachelor's of Science honor in mathematics from St. Columba's College, Ranchi University, followed by an MSc in applied mathematics from the Roorkee University, where he secured first rank and a university gold medal. He further earned an MPhil in computer applications, again standing first in the university, and completed his PhD in applied mathematics in 1992 with a thesis on vibration and computational methods, which was adjured meritoriously. His early academic brilliance laid the foundation for a career that seamlessly integrates mathematical theory with real-world engineering application. He pursued postdoctoral research at two premier international institutions, the Institute of Sound and Vibration Research, University of Southampton, UK, and Concordia University, Canada, with his additional academic engagements at McGill University. These experiences significantly shaped his research in computational mechanisms, vibration analysis, and numerical methods. He later served as visiting professor at several leading universities worldwide, including Johannesburg University, South Africa, and universities across Europe, North America, Africa, and Asia. With over 35 years of combined teaching, research, and administrative experience, Professor Chakravarti has made seminal contributions to applied mathematics, artificial intelligence, soft computing, and dynamical systems. He has authored an exceptional body of scholarly work comprising over 350 journal publications, over 160 conference papers, 39 books, and 70 plus book chapters, and hold patents in applied computational technologies. His research has been widely cited, placing him among the top 2% of scientists worldwide in artificial intelligence and image processing for multiple consecutive years. Professor Chakravarti has successfully supervised 30 PhD scholars, guided numerous postgraduate projects, and hosted international visiting researchers. He has led 22 sponsored research projects as principal or co-principal investigator, and continues to mentor young researchers across disciplines. His work bridges rigorous mathematical foundations with emerging paradigms in machine learning, uncertainty modeling, and fuzzy dynamical systems. An accomplished academic administrator, Professor Chakravarti has held several key leadership positions at the NIT Rokela, including the Dean Academic Affairs, Dean Student Welfare, Professor advising the Director on Finance, Head of the Department of Mathematics, Head of the Central Library, and Chairman of multiple statutory and academic committees. He has also contributed nationally as an external state member of the NIT Padrish and the NIT Agatha. His role in shaping institutional policy includes chairing the formulation of NIT Rokela's anti-plagiarism policy and the implementation of the National Education Policy NEBP 2020 framework. Professor Chakravarti's professional recognition are extensive and prestigious. He is a senior member of the IEEE, president from 2015 to 2016 of the Mathematical Science section of the Indian Science Congress Association, and the recipient of numerous national and international awards, including the CSIR Young Scientist Award, the Careers 360 Faculty Research Award, and multiple IOP Publishing Top Cited Paper Awards. His scholarly impact has also been acknowledged by Scholar GPS, ranking him in the top 0.0% of scholars globally in vibration and physical sciences. Widely sought after as a keynote speaker and invited lecturer, Professor Chakravarti has delivered lectures at more than 50 international and national universities and conferences. His current research interest focuses on mathematics of machine learning. Thank you. You're welcome, sir.
No, thank you. Thank you for introducing. So thank you for giving me the, I think I'm audible. Yeah. Am I audible?
Yes.
Yeah. Yeah. So let me share my screen. Okay. Is it visible? Is it visible?
It's coming up.
Yes.
It's coming up.
Yeah, good, good.
Yes, full screen. Yeah,
Yeah, it's fine.
it's coming up.
This is fine.
Yes, it's fine. You can go ahead, sir.
Okay.
Yes, sir.
Okay. So first of all, thank you very much for giving me opportunity to present my this research topic. So and thank you for so elaborately mentioning about my credentials and citations, etc. Thank you again, and very good morning to all of you as per your place, and very good afternoon in India. So anyways, so I will just light upon as the title is shown here, that is Machine Learning in Dynamical Systems, a mathematical journey from exact to fuzziness. So here actually I will try to ignite your minds in different directions of your mathematical modeling, namely in machine learning that may be applied to different dynamical systems. And also I will light upon the fuzziness of those systems, means uncertainty of those systems. Okay. So first of all, if you see about the nowadays artificial intelligence, everybody knows more or less. So this is actually the bigger set. So in that we have machine learning. So we have different types of machine learning. Okay. So those are, suppose, artificial neural network. Then you have SVM, support vector machines. Then if you go to optimization techniques, then we have genetic algorithms, then swarm intelligence. So there are many. So it is a combination of all these learning methods. Even statistical learning, those are there in machine learning. So in machine learning again comes one, that is one method that is called artificial neural network. And in artificial neural network, we have a special type of learning, that is deep learning. Okay, so mainly I will be focusing on artificial neural network models that will be used to solve different types of dynamical problems. And those dynamical problems are actually coming from, the governing equations equations are the differential equations, and sometimes those differential equations can be converted to eigenvalue problems in general. Okay. So, and moreover, you'll see that some uncertainty also I will take in those parameters, and then how to handle using the machine learning, namely uncertain means artificial neural network, how it handles the uncertainty in the problems, that also I will show you. Okay. So with this, the main means topics will be these ANN, and you know that ANN actually, that is artificial neural network, is actually the machine learning means we have the natural neural network in our human body, and that actually is being mimicked in computer. Means scientists trying to mimic those neural networks in computer, and then it is called artificial neural network. So there are actually various applications of this artificial neural network, namely in variety of problems. Nowadays, each and every many areas actually these machine intelligence or neural networks are being used, such as in physics, chemical, medicines, finance, and there are many. Some of them I have written here. And few recent applications include also astrophysics models, buckling analysis that is related to civil and mechanical engineering, then inverse kinematics problems, etc., etc. Okay, so ANN is actually key component sometimes for dynamical solvers that I will show you after a few minutes. So this is the actually figure of a basic model of ANN. So if you see, so here actually what happens, these x1 to xn are the parameter of the problem. Okay, so if I have n parameters, input parameters, and final output parameters is z, so if I have data, suppose n input data and 1 output data, then the artificial neural these nodes I can generate like this: y is equal to b is bias, and bias plus the summation of this xi with some weights for these connections. Suppose from x to this bias term, so it will be b plus summation xi wi, that is your y. So it is a simple means ANN model. Okay, that's a simple model. So error will be this half into summation target output, means I have the final output exact data and final output from this model data. So this I subtract and square and sum for all those data. Okay, so this is the error. If this error is not satisfied, then again I will go here in this means this weights I will change. Okay, suppose W1 plus delta W1, or there are actually procedures to change this. And again, I will find this Y for this model and go on this finding these errors, and will stop when this error is minimized as per your means desire. Okay, as per the means requirement of the problem. So this is the just simple model. So actually there are many things. Actually in this short time I cannot mention all those things. So this is only one actually. There is no hidden nodes or hidden layer. Okay. So you see now ANN architecture are different types, maybe feed forward or feedback. So the left side figure 1A, the feed forward neural network, and right side figure is feedback neural network. See here, this signal flows from these nodes to the last nodes. Here you see the signal flows last nodes. Again, it also gives in the previous node. So that's what is feedback neural network. And we use here activation function. So activation functions are also various types. That is identity function, Gaussian function, sigmoidal function, tangent hyperbolic function, rectilinear, linear unit. There are many. Okay. So actually in my work, I have used these two: unipolar sigmoid function, this is the figure, and this is tangent hyperbolic function. These two types of activation functions we have used in our work. So learning rules, as I told, there are learning rules. So we have supervised and unsupervised. Supervised means when I have output data, I have a teacher, so I know the output, but I have to fit those data. That is called supervised. I can fit by regression also if those people who knows about the regression. So actually this is similar type of regression, but not exactly that regression. Okay, so as we have in regression method, we have input and output data. Here also supervised, we need the input and output data. And then the unsupervised, that means learning without a teacher, means I don't have any output data. Suppose I want to solve a differential equation. So I don't know the actually the solution of that differential equation, but I know the initial or boundary condition. So using those conditions, we can solve that using artificial neural network or machine learning using unsupervised learning. Okay, so this is the difference between supervised and unsupervised. Now there are various types of learning rules you can get in many of these books. All these I am not going into these details. So maybe Hebbian learning rule, perceptron learning rule, delta learning rule, then other two. There are many others also. But in our work, we have used delta learning rule or back propagation rule. So now I will show you a simple problem of solving transcendental equation. Okay. So I hope you know what is transcendental equation. So I have a single equation, a1 phi 1 plus a2 phi 2 plus up to n pi n is equal to c. Simple one variable single one-sided transcendental equation. So I will make this means architecture of this ANN like this.
Yourself, sir. Hello, Prof. Your mic is muted. Can you kindly unmute yourself, sir? Hello, sir. Your mic is muted, sir. Kindly unmute your mic. Yeah, yes, sir. Carry on. Your mic, sir, is muted. Kindly unmute.
Yeah, this is okay. Fine.
Yes. Okay. Okay. Go ahead, sir.
Yeah. Okay. Just a minute. Yeah. So it's okay now. You can hear. Yeah. Am I audible?
Yes, sir.
Yes, sir. Go ahead.
Yeah. Yeah, so this is the model for the single transcendental equation. So I will now show by an example about this latter. So before that, if you have system of transcendental equation, means I have a n number of equations. You can see I have a11 phi 1, a12 phi 2 up to a1 and phi n with all additions is equal to c1. Next equation is a21 phi 1, then a22 phi 2 like that. Means phi 2 means phi x2. Phi 3 means phi of x3 like that. So is equal to C2, and last equation is an1 phi 1, that is an1 phi x1, then an2 phi 2, then up to an and phi n is equal to Cn. So this is system of transcendental equation. N equations and n unknowns. Then I will make this architecture like this. So you are seeing here this layer having n variable x1, x2 up to xn, and these phi i's I have like this phi 1 to phi n. Okay, so then I have, depending upon what are the coefficients here, a11, a12, so we'll put these as the weights, a11, a12, etc. Okay, then we train this using delta learning rule, and I can solve this transcendental equation. So this is through machine learning. Okay, so this I can show you now by one example, simple example. So if we consider this transcendentally one equation, single equation, cos square x minus x is equal to 0. So I can put this ANN architecture like this. This cos square x here, this x here, and the coefficients are 1 and minus 1, 1 and minus 1. And this first is, this is the x to this cos square is x as weight 1, and x to x, this is 1. So like that I can train and I can solve. And in this figure 6 in the below right hand side, you can see the convergency plot of the root of the transcendental equation. Okay, so this is actually, if you see in the next slide, sorry, so So this is actually the root is, if you can see which has a root of this equation, exactly you can find by other method, Newton-Raphson or other method. So 0.6417. So if you can see here, this root is 0.6417. You can see the figure. It is exactly, it is actually matching that, and convergency comes after 200 epochs. Okay. So in this way, simple non-linear, this transcendental equation I can solve using neural network. Okay. This is just a simple example, means using ANN or machine learning. So if I now have, means this I can also solve in like that. I solve you the theory system of equations also. So I'm not showing that due to the because we have already solved these things, and the papers are available corresponding to this. So I'm not showing you all those examples. Okay. So now coming to eigenvalue problem. Suppose I want to solve eigenvalue problem like this, which is actually dynamical system, this mx double dot plus cx dot plus kx is equal to 0. So dynamical systems, we got this type of differential equation. This is a coupled second order ordinary differential equation. This M is a matrix actually, and this C is also a matrix and K is also a matrix. This M, as per the structural problem, this is called mass matrix. This C is called damping matrix and K is called stiffness matrix. And there is a pattern of this matrix depending upon the problem. By the way, this for this structure problem, this is just a diagonal matrix having the elements M1, M2, means the mass of that problem means that n degrees of freedom. So these are the masses placed. Okay. Similarly, this damping matrix is tridiagonal matrix, and stiffness matrix is also tridiagonal matrix. Okay. So this is the problem that I want to solve using neural network. Okay. So if I don't have this damping, so this equation 5.1 can be converted to 5.2. That is only mx double dot plus kx is equal to 0. So this I can convert into eigenvalue problem, putting x is equal to phi to the power I omega t, considering that this follows simple harmonic motion. And so it leads to a linear eigenvalue problem given by equation 5.3. Ax is equal to lambda x. Now I want to find this lambda. That means I want to solve this eigenvalue problem, where lambda is eigenvalue and x are the eigenvector. So both eigenvalue and eigenvector I can find using this machine intelligence technique. So if I expand this after putting the A elements, so what I will get, that everybody knows, means this will get a characteristic equation of nth degree depending upon the order of the matrix. Okay. So this way I will get this as the characteristics equation. So this is again actually a equation depending upon your A1, A2, A3, An, these coefficients. Okay. Nth degree equation. So this I can solve like that. I have already shown like this, putting this lambda, lambda square, lambda cube, etc. in this layer 3. And this I was earlier putting x here in place of x, it is lambda. So I can have put here lambda, and like that A1, A2, A3, this coefficients I put these are the weights, and from this input layer to the middle layer I'm putting all these at 1. And again, if I can solve, if I solve this neural network, so I will get I will get the solution. Okay. So now coming to an example. So suppose I have this 3 degrees of freedom system. So this, these are the masses of 1 kg, 2 kg, and 3 kg. I have different spring coefficients. So this, if we do the physics of all these, so I will get A, that is M inverse K, because I have already found, I've shown here, see, here it is M inverse K. This is I have put as A, okay? So M is mass, K is stiffness. So M inverse K. So this I can have for this example like this, is M inverse K. So this matrix comes out to be this. So this is a third order matrix. So I will get the characteristic polynomial as 3 lambda cube minus 11 lambda square plus 10 lambda is equal to 2. So it is third degree equation. So now I can put this in the ANN architecture like this, because I have lambda, lambda square, and lambda cube. So I have lambda, lambda square, and lambda cube in the third layer, and these are connected to the output node as the coefficients of these. Okay, so these are lambda coefficient is 10, so here 10, lambda square coefficient is -11, so it is -11, and lambda cube coefficient is 3, and the input layer to middle layer or hidden layer, the weights will put arbitrarily as 1. So if I train this, so I can get the solution. So if you can see this table, so these are the actually the solution. Okay, if you see the last column, so these are the eigenvalues. Okay, because we need in ANN different parameters, so learning parameters, stopping criteria means I already told about the error up to which we should run the program. Okay, and initial weights also we have to give. So these are the initial weights. So lambda 1, lambda 2, lambda 3. Finally, I got 2.3874, 1.0, 0.2792. And these are the epochs where these eigenvalues when it starts converging. So in this way, I can find just an example. I can solve the dynamical problem with respect to the structural problem that I have shown you. Okay. And correspondingly, eigenvector also we have found for lambda 1. This is the first eigenvalue. Lambda 2, this is the second. And this is the third. For the third eigenvalue, this is the eigenvector using the same procedure of NN. Okay. Now coming to actually an application problem. Suppose I have a 5-story building, okay, shear building. Okay, we assume that these are the assumption just that story masses are M1, say first story, second story, third story up to 5th story. So these are the masses, suppose given as M1 as 30 kg, M2 as 27 kg, like that. And these walls I will consider as springs, and those spring constants are K1, K2, K3 up to K5. So this is I will get then the matrix as 5th order. And if I have the characteristic polynomial, which is 5th degree, now this again I can put in, as I already told, this I can put in an architecture and I can solve. And the solution for these eigenvalues are like this. In this table 3, the last column gives you 5 eigenvalues, and the figures, these are actually with respect to the convergency of these eigenvalues. Fine. So these are eigenvectors for the 5 eigenvalues that also we have computed through ANN technique. Okay. So now see these, what we have done till now, we have just got the eigenvalues, that means frequency of the system. Now I will show you a practical, practical problem with respect to civil engineering, that is response prediction of multi-story buildings subject to earthquake motions using artificial neural network. So what happens, you see, when somewhere earthquake triggers, so what happens when earthquake triggers, here different types of waves travels through the soils. Okay, soils means in soils we have different types of means rocks, sands, and metals, or maybe coals or ores or whatever is there in the soils. So these waves travel through these soils, okay, through the ground and comes near to the building. Suppose there is some structure. So whatever waves it will travel, so it will now change when it will come to the structure. Okay. So now these waves, there will be a soil and structure interaction. So as per American Society of Civil Engineering, till now there is no mathematical model which can actually handle or which can predict that what this means. This suppose what will be this soil and structure interaction means what type of wave or what will be the acceleration of these waves in the building or the structure. So that is very difficult to obtain. Till now it is not there, that model exactly. Okay, so here we can use this artificial intelligence or neural network in the machine learning. If I have here the sensors or some equipment, I can measure the waves here, and I have the equipment here with sensors in the building. And what are the displacements here? Now these are the suppose input, and output is the building sensors. So I can play with those, and then for different earthquakes, future earthquake, I can predict by what this displacement will be by what amount, so that I can develop an earthquake warning system. Okay. So that thing actually we have actually did little bit of work on that direction. So we have taken exactly the actual earthquake data. So in India there were several earthquakes. Okay. So these types of earthquake data we have taken. So see, this is the multi-story structure, tall building, and this is a Chamoli earthquake, Barkot in Himalayan region, it is there. Okay, so this peak acceleration is 19.588 centimeter per second square. So this type of earthquake, it triggers on the ground. So when it travels to the structure, this is change actually. So suppose here the some equipment is there which can means capture the displacement of these flows. Okay, so if I have those displacement and this displacement or acceleration, whatever, so if I play with that, then I can fit that, then you can predict for different earthquake, other earthquake or some other magnitude earthquake, what will be the displacement or acceleration of this structure or building for this case. So for this some mathematical modeling, here it is the equation 1. If you see, earlier we have seen mx double dot plus kx is equal to 0. Right hand side was 0 because there was no force. So now it is minus ma double dot. A double dot designate the acceleration for the that earthquake. Okay, so if I model this, I will get this equation 2, and this I can solve using this Duhamel integral, we call it. So this I can solve and find the displacement. So actually, see, for we had the measurement, or we had the data for the earthquake, but not the data for the buildings. Okay, so this building displacement we have found using this model. Using here, you see inside that I have the earthquake acceleration, and this is sine omega t minus tau. Omega is the acceleration, natural frequency. Okay, natural frequency of the structure. So I can find this integration, and then I can play with this input and output data. So this earthquake we have taken as the input, and different types of earthquake also we have taken, Uttarkasi earthquake, Chamoli, Bhuj, etc. So then we are actually, I am not going to show you all those work, just some representative problems or figures I will show you. So this is the multi-story shear building, suppose. And these are the parameters. Parameters means mass matrix and stiffness matrix. I have already defined. So these are the mass matrix where this 6,000, I have taken all the masses of the stories as same. And this is the stiffness, okay, Newton per meter. And using that model now, if I have input output as the acceleration of the earthquake input and output at the acceleration of the building for different story. Now, if you can see the top figure, that is 8th floor. So I can find the actually exact acceleration also we have found using some numerical technique, that finding this integration. Okay, and then using that we have found the ANN acceleration, and then we have plotted both, but you see the beautiful matching. Okay, although we could not go actually in some of the peaks, but at least the trend it is gaining, okay, using ANN. And this figure is for 8th floor. Okay, similarly, if the lower one, bottom figure, it is for 6th floor. Similarly, we have actually simulated many problems, maybe other stories also. Okay, so this is another for 80% of the earthquake. Here it is 120%, means different means magnitude, means whatever, suppose I have 6.0 magnitude, then from that we have computed 80% of that, and then we trained, and here it is 120% of that. Then how it behaves, or how it actually gives the trend for that acceleration, that also we have predicted, okay, using that. So these are not that whatever I am presenting, it is not that fully whatever models and step by step I am not showing, because it will take much time. I just want to try, I want to trigger your mind that this machine intelligence can be used in these directions, in all the dynamical problems, whatever. If you have the data or you don't have the data also. Without data also, we have solved directly the differential equations, but I think that I am not showing in this lecture, but those things also we have done. Okay, so this is for some other earthquake, okay, in another direction, any direction like that, and using different actually errors also we have plotted, errors and without damping. So those things also we have done. So till now, whatever we have seen, that was without any uncertainty. As you know that in our day-to-day problem or other problems, we have uncertainty in all of the problems. Whatever problem you take, there will be uncertainty. So uncertainty can be handled by many ways. So one way is this interval and fuzzy, and another is that probabilistic or stochastic. Okay. So we have not used probabilistic or stochastic. We have used here interval and fuzzy, and that too interval and fuzzy in the neural network. That is why we are calling this as interval and fuzzy neural networks. And again, we will case study with some dynamical problems with respect to structural dynamics. Okay. So and moreover, why we have used this interval and fuzzy, when actually you have less number of data, then we should use the interval and fuzzy. If you have large number of data, then you can use the probabilistic or stochastic analysis. Okay. So I'm not going into these details, just few things. Interval, actually, all the data suppose in interval form, if you see the data, suppose x is your some variable, so I can have x lower and x upper, where x lower less than equal to x less than equal to x upper. So this x will be in between lower and upper value. So remember, this left side is lower value and right side is upper value. So now we have specified addition, subtraction, multiplication, and division, means formulae or definitions. So if I want to have two addition of two intervals, so this is simply lower lower and upper upper. But if you subtract, then it will be a little bit different, lower minus upper and upper minus lower. That is why if I subtract x minus x, means suppose two intervals, same intervals, we subtract, then we will not get 0 0. Okay, and that is the problem with this interval computing. Okay, although this is very means very challenging with respect to your practical problems to handle uncertainty, but this x minus y and this x by y, means x divided by y, is also a problem, because if you see this x divided by y, we do this, but where we assume that this y tilde should not belong to 0, means 0 should not belong to this y tilde. Okay, so these we have to take care before applying this interval computing, and that too in NN, so it will be a little bit more difficult. Okay, so then comes to fuzzy set. Fuzzy set also a type of uncertainty. So this is an ordered pair where we have element and its membership function. Okay, and an interval actually is a subset of fuzzy set. And we then comes to fuzzy number. Actually, fuzzy number is coming from fuzzy set, a special type of fuzzy set where the membership degree is convex, normalized, okay, and piecewise continuous. So we have different types of fuzzy set, okay, fuzzy number. So we have used some particular type, okay. So like triangular fuzzy number. So the shape is of triangle, if you see, and we write it as ABC. And that ABC can be written in terms of interval. That is why I have first shown you the interval definitions. So this fuzzy number I can write in terms of interval. So then that means we need to have the interval computing. Now this is another type of fuzzy number that is called trapezoidal fuzzy number. The shape is of trapezoidal and we designate by ABCD. You see here ABCD. Again, this fuzzy number also can be written in terms of interval, and then we can handle with interval computing. Okay. Now coming to the same type of problem, that is multi-story structure. So you see here earlier the masses, if you see earlier it was in this mass matrix as M1, M2, Mn. Now you can see here I have in interval form M1 lower, M1 upper, M2 lower, M2 upper, up to Mn lower, Mn upper. This means these are uncertain form, having lower and upper values. Similarly, I have K matrix also, stiffness matrix, that is also in terms of uncertainty. Okay, so interval form. So after substituting, supposing that simple harmonic motion, etc., will turn into again to an eigenvalue problem. Like this: K minus M omega square phi is equal to 0, and see every all these matrix and whatever parameters I am using, all are with tilde. That means all are in interval form. Then your that's ANN model. That is, now it will be interval neural network model. So here, if you see the left hand side, these are the inputs. Again, these are all uncertain form. That is lambda 1 tilde, lambda 2 tilde, lambda I tilde. Here it is K1 tilde, K2 tilde, KK tilde. Here the problem is knowing this frequency or the eigenvalue, what is the stiffness if I want to find. So in this way, I can have the neural network architecture, and using those data, I can find what is the stiffness. Okay. So similarly, for fuzzy case, we will have actually in terms of this interval, means converted interval from the fuzzy, and I can handle this uncertain case. Okay. If you see again here in the figure, you see here mass is here, not only M1 lower and M1 upper, but I have another element here, that is M1C center. Okay, because I have taken triangular fuzzy number. So all these masses and stiffnesses, I have three components. Although those we have converted to interval form. That is why in the mass matrix, I have interval form of these elements. Okay, M1 lower H, M1 upper H, like that. Similarly, K matrix also I can write in terms of interval. Okay, like this. K, this is the K matrix. So if I again do the all calculations, etc., I will come into this equation 3.4. That is again an eigenvalue problem, but having this interval form. Okay. So this is the fuzzy neural network. I have now in terms of H actually designate that conversion from fuzzy to interval. Okay. So lambda 1 H2, lambda IH, depending what is your I. Okay. And these are the hidden nodes, hidden layer. In the hidden layer, I have, these are the nodes, and this is output layer. Okay. So if I train that, then again I can find for different unknown frequency what is the stiffness. Right. So now I suppose I take some example. So if I take, suppose it is a 5-story with uncertainty, interval uncertainty. So K1, K2, K3, etc., K4, K5. Suppose we take like these elements, lower and upper. Okay. And then if I train, etc., so these are the trains for different data numbers. So these are the K1, K2 we have means computed. Okay, K1 to K5. Fine. So you see here the solution is K1 n and K1 desired, K2 n and K2 desired, etc. We have found. So this is the result. So now coming for, oh sorry, this was actually in CRISP case. When we did the CRISP, so we took the center value. Okay. Now next figure shows the interval one. So this is the interval case. So this is, see, left side figure with lower values, and right side figure, left side figure is lower and upper for K1, and right side figure is K2, means second stiffness for lower and upper. Okay, and the comparison between desired and neural network, and see the trained and the data means data matching are good with respect to your NN and desired. Okay, and this is again for K3, K4, and K5, because it was 5-story building. So we had 5 stiffnesses. Okay. So this is for testing. After training, suppose I take some new value of these interval stiffness are taken. So these are the comparison. Okay. So this is fuzzy case. Fuzzy case again, I will take as this same data. Okay. So these are the fuzzy case comparison for K1, K2. So here you see K1 lower, K1 lower desired, K1 lower fuzzy neural networks result, and K1C, that means center value. Okay, for desired. K1C for fuzzy neural network, like that. These three are there, lower, upper, and center values. Okay. So now testing for fuzzy case. These tables are for testing for this fuzzy case. So we have tested for those data which are not used in the training. Okay. So what actually till now what we have done, actually these just representative results we have shown here. We have simulated for various cases, various actually practical whatever means problems also we have done. Okay. So using different earthquake data also we have done. So in the conclusion, so you have seen that ANN models are means actually dynamical solver. As a dynamical solver we can use. We have used means we have compared the traditional neural method, numerical method, and ANNs, and you can see that ANN is computationally efficient. Okay, and the model is messless, because if I solve by different problems using some other method, suppose finite difference or finite element method, those are we have to use messes and all. Here we don't need mess. Okay, so it is like a black box. If I train the neural network model, and then if I give the input data, new input data, then it can predict approximately what will be the output. So that is the actually benefit of this machine learning. So okay, so due to the nature of the neural network, the CPU time for finding the solution of the given equation does not increase exponentially with increase in dimension. There are many things. I am not posing those things anyway. So these are some references, okay, that we have followed. Okay. These are actually some books that we have with my students. Actually, we have written. That is, first one is Artificial Neural Network for Engineers and Scientists. So in that book, you will get all solving ordinary differential equations, how to solve using neural network and all. And the second one, Applied Artificial Neural Network Method for Engineers and Scientists, solving algebraic equations. In this book, you will get different types of transcendental equation, eigenvalue problem, even nonlinear eigenvalue problem also we have solved in this book. Okay. So these are the two books, one from Taylor and Francis, CRC Press, other one is World Scientific. And then we have, this is actually concepts of soft computing. Here we have included some programming also related to fuzzy and ANN. Okay, there we have used the uncertainty, etc. And this is the soft computing in interdisciplinary sciences. This is edited book. This is not, those three are authored book. And this is one journal that is we are actually I am the chief editor of this, Fuzzy Computation and Modeling International Journal, published by InterScience. Okay, and thank you for your attention. Just I have gone through the models actually regarding all machine learning techniques with respect to artificial neural network. I tried to ignite your mind at least that this can be used in any other problems also, where you have the differential equation or you have the data. You can use very well, but again, it depends upon how you take the what optimization techniques you are using, how many nodes you are taking, how many inputs you have, how many output you have. There are many things to play in that with that actually in the simulation it requires. Then about main thing is the weights, how you are generating, and what type of learning algorithm you are using. So there are many challenges now. Actually, now we are working in physics-informed machine learning also. Okay, where we have used with data the physics of the system. Okay, that I have not actually presented here. So if I get chance in future, I can again detail about that. Okay, thank you very much. I hope you enjoyed. So if you have any question, you can ask.
For that beautiful presentation. Thank you very much, sir. All right, so we're
Thank
going to take questions, one or two questions based on the presentation. So other people who want to ask question or engage Prof on this presentation, either online or on site. So we're going to take out people who want to engage Prof or ask questions based on this presentation. Anybody online? And on site. So if you have questions, just signify by raising up your hands. So capture that. Anyone? Question? Okay, we have one. Then any other one? Question? Feel free to ask question or engage. Okay, let's take the number 1% word. Okay. Yeah. Thank you.
Prof, thank you so much. It's such a
thank
very
you.
interesting presentation. My question is this: in vibrational resonance, how does it relate with earthquake and putting stochastic resonance to what? Yes, stochastic resonance. Stochastic resonance. What is the relationship in taking their wavelength and frequency? Thank you, sir.
Yeah. Prof, did you capture that?
Yeah, can I reply? Yeah.
Yes, you can. Go ahead, sir.
Yeah,
Go ahead.
Actually, you are asking about stochastic and wavelet. You are asking.
Yes.
Okay, so stochastic, yeah, actually stochastic neural network is there. Wavelet neural networks are there. Okay, so those are the actually little bit different way it is being trained. Actually, it is not like that. Whatever I have actually explained. Okay, so stochastic neural network is there. Okay, you can use that directly in Python. Also, you can get those things. Okay, so there the differential equation etc. will be stochastic. Okay, so those things we can handle, but not the way I have presented. Okay, the procedure will be different. Similarly, wavelet neural network is also there. Okay, we can use that we have not actually done in our research area. Okay.
Okay. Prof has a question. All right.
Thank you very much,
Yeah, thank you.
Professor Chakrabarti.
Yeah.
So my question has to do with like for Fuzi, you are dealing with possibilistic approach, and then for stochastic, you are dealing with probability approach. Now, like going by your presentation, you have applied this to mainly vibration, earthquake, and all that. Now, like I don't know, have you thought of like you gave a fusified differential equation? Now, have you thought of using stochastic differential equation and comparing the results of fusified differential equation and stochastic differential equation, either Ito or Stratonovic or approach, depending. Thank you.
All right.
Yeah.
Prof, you can go
Yeah.
ahead. Yeah.
Yeah, that is an interesting question. Actually, yeah, we have actually solved the stochastic differential equation also using this neural network. Okay, and the fuzzy differential equation also using neural network. But those problems are different. We have not compared with fuzzy differential equation with stochastic because these uncertainties are different. Okay, because probabilistic there will be PDA, probability density function, probability mass function, etc. But in fuzzy, those functions will not come into picture. And the fuzzy, I already told that when you have limited number of data, then you use interval or fuzzy means uncertainty. So actually we cannot compare like that. But yes, you are correct. Suppose I have 5 variables in the problem. So maybe 3 variables you have less number of data. You take those 3 as the means fuzzy, and other 2 may be as stochastic. Okay, but till now these two combining this fuzzy and stochastic or probabilistic is not actually systematically done. That is an open problem, how to combine this stochasticity and fuzzy. Okay, but separately we have done. Okay, I hope I could explain something. Yeah.
Thank you very much, Prof. All right. So, Prof will give a remark.
Yeah,
Thank you very much, Professor Ashish Chakrabarti. Yeah, we want to appreciate you for coming. I met Professor Chakrabarti in 2014 when I was in Sri Lanka. I went for a conference, and in the course of the conference, he just I think I stayed with one of his students. So the student introduced me to him, and then he just called me and said, Bakare, do you want to come to India? I said, yes, I would love to come to India. I was sitting. So, and the next thing, he got back to India, he sent me a fellowship program that's a research training for developing country scientists. So, by the government of India. So, I applied, I wrote a proposal. That was one of the first proposals I wrote in my life as a PhD student. So, I wrote the proposal. Then, when I gave the proposal, I sent the proposal. So many Nigerians were in that when they did the shortlisting. I was shocked. So he called me and said, "Oh, Bakare, why is Nigeria too much in this list?" See, even me, I don't know. I thought that I'm the only one with the information. So at the end of the day, I saw doctors, professors in the list, and so I said, "Wow, I don't know whether I'll be able to make it because this is a very hot list." So, but eventually, at the end of the selection, I was the second person selected in Nigeria for that grant. So I was with him for 6 months in India, and that was where I finished my PhD. So and then he was my teacher on interval analysis. So I applied interval analysis in I have a paper on interval analysis applied to epidemiology. So for 6 months, I produced 6 good papers. Yes, I was sleeping in his office, the next office is my office. So he's a very hard worker. Yes, he's a very hard worker. So I was sleeping, sometimes I was sleeping in his office, sometimes he would bring me to his house, and then the wife would cook for us, we'll eat, and he will encourage me. Some people will tell him that, oh, Bakare normally sleep in the office. He will say, leave him. He came here to work. So eventually, when I finished my 6 months, he asked me that I should come back, that I should apply for project. I want me to come. So I applied for CV Raman.
CV Raman.
Yes, I got CV Raman, but there was another one that came also twice. So I had to pick between the two. So I didn't go. So, but I'm still coming back to HITE again to meet you in your lab. Now, the thing about him is that, sincerely, there is no time I check online. LinkedIn is always very challenging. Even as a professor for several years, he's still publishing. Yes, he's still every year he's publishing. Now, you cannot pay a professor unless you are still working. If you don't publish, your professorship can be taken away. Yes. It's Nigeria, somebody say a professor, then you don't go for conference, you don't go. There's nothing like that. He's still, you see that some of us, we are running after him. Sometimes there was a day I saw him online and say, this thing you are published again. I said, God, oh. So he's challenging us. So anytime I see him, I said, no, I mean, these are people I want to follow. I don't want to follow somebody that's not doing anything. That I'm a professor does not mean that I've gotten the climax. And as Professor Chakti is 60 years. Yes. But he's still working very hard. I remember that time when I was doing my working with him, there was an earthquake in Nepal. So that was the first time I learned safety. You know, he taught me safety. Now, as soon as this earthquake came, you know, the building, we're in the 6th floor, 6th or 5th floor. The building shook. So it was coming. So we went downstairs and then we stayed in front of the building. So everybody stayed. So I said, hey. So safety first. I was thinking of my laptop, my book, he said, no. So I appreciate, you know, my time in India was very wonderful because it was a very great mentor. Until today, we still relate. This is more than 10 years now. We still relate. More than 10 years. For him to still come around, he tells me that anytime I have conference in Nigeria, I should invite him. Although he cannot come physically now, I know that maybe next year he's going to come. By the time I inform him earlier, am I saying something?
Yeah.
Okay. So thank you very much. What do I say in India? Namaste, namaskar.
Namaste. So thank you, Bakare, for
It's like there is a thing for publishing this paper in India. So, Prof, I think after now, Prof will second me to Mr. Chakravarti, so that by the time I come back after six months, 6 papers.
Yeah.
All right. Thank you very much, Prof. I appreciate you.
Thank you very much. Thank you.
All right.
Thank you.
All right, let's
Bye.
for him again.
Yeah. All the best. Yeah.
All right, so this time around we'll be going for a tea break. So okay, now you know. Okay, we'll do now you know, then we'll go for tea break.
So I'm leaving then.
I'm leaving, please. Coordinating now you know. Okay.
Okay.
Yeah, you can leave, sir.
Okay.
All right, so we'll do now you know, then coordinating us, Mr. Jim. Mr. Jim. Coordinate us. Okay, Prof. All right.
Stand up.
Good.